and I'm going to let Tim introduce his talk, and I am really looking forward to it.
Thank you, Melinda. I will say it's fun to come here. I guess I've been coming maybe a year and a half or so. It's fun to come and actually know people, which I didn't for a while, but I know a lot of faces and even some names now, which is exciting. If this works, it would be great. Okay. Oh, errors already. So, well, I guess back to this first slide. I actually made these slides in an IPython notebook, which I'm happy to tell you more of what that means later, if you don't know what that means. But it's the first time I've ever done that, and last time I gave this presentation with code in it. I was copying code into PowerPoint, and it ended up being filled with errors and discrepancies and various things. So this is pretty cool because all these slides are actually runnable code, and you can get the notebook on GitHub and actually run everything in here runs. This is a new feature in IPython 1.0, which if you use IPython you probably have by now, but it doesn't work in 0.13, which was the older version. As of Monday, I'm a software engineer at a startup called Parsley. We do analytics for news websites. As of last week, until last week, I was a data scientist at RTI International. My old boss Gail is here, and she's hiring, so if you're looking for a job, come talk to her. If you know some Python, she'll be very excited to talk to you. And she's a very nice lady, so you should talk to her anyway.
And I didn't fire him.
She didn't fire me when I left. She, in fact, almost cried when I left. So.
I did.
What is Scikit-learn? It's a machine learning library in Python, and we'll talk a little bit more about what that means. Brian Shepard is here and
already. Wow.
Has comments about how he doesn't like Python. And so to appease our programmers, I'm going to start off by saying that Scikit-learn is as if Hadley Wickham had written a machine learning library for Python. It's dissatisfying to use from just the nice software as using Hadley Wickham's tools in R. So hopefully that'll calm Brian down a little bit. So these are the categories they give for what Scikit-learn does on their website. I apologize for the text size. There's really nothing we can do, but classification, regression, clustering, dimensionality reduction, model selection, and preprocessing. One thing we'll talk a little bit about is that Scikit-learn has incredible documentation. I know people, in fact, who are kind of teaching themselves machine learning by going through the documentation here. And these are breaking down those categories. Oh, bother. Okay. So why Scikit-learn? This is plagiarized straight from a pretty good blog post, I think is on the O'Reilly blog. 6 reasons why Ben Lorica likes Scikit-learn. One is commitment to documentation and usability. Usability is really what I want to talk about now, is that it's just a really nicely designed piece of software, but the documentation is also excellent. As he says, it's something for others to emulate in the open source community. There are models chosen by and implemented by a dedicated team of experts. Some really smart and talented people are developing Scikit-learn, and a number of them have PhDs in machine learning. A number of them are PhD students in machine learning. I meant to get a link in here to the list. There's a list on GitHub of contributors, but it's a very smart group. If you're on Twitter and you're interested in Scikit-learn, find some developers and follow them. They're very active on Twitter, and they're very interesting to follow. Scikit-learn covers most machine learning tasks. This maybe would be debatable. For, among other reasons, defining what a machine learning task is very hard, but it does a lot of machine learning. Arguably, one limitation is not a lot of neural networks stuff. You can decide for yourself whether or not that's a limitation or a blessing. But there's minimal neural network implementation, and thus minimal deep learning implementation. But from a more traditional machine learning data mining perspective, there's a lot in there. Python and PyData, really just that Scikit-learn is built in Python, which is a general purpose language, which arguably sets it apart from R as a more domain-specific language. Python has a very, very robust library, open source library selection that you can, so you can not only build your machine learning library, but you can build your web server to deploy a website that runs this machine learning model that you want. And you can do natural language processing. You can build a GUI on your computer if you want. I mean, you can, in theory, do almost anything from just a general programming perspective with Python, and you can embed Scikit-learn in that, in theory anyway. And then PyData, more specifically, Python over the last few years has really grown in terms of specific tools for data analysis and data manipulation. The pandas library, if you've been around Python at all, you've probably heard about, if not used, as a data frame implementation, sort of copying what R has natively and then extending it in some ways, though there may be some limitations in that it's not a native data structure like R has with data frames, but it's a very, very powerful tool. There's some amount of plotting libraries for Python. I think that's still an area where R is doing better, but that's a really fast changing domain, and it looks like in the future we'll have sort of cross-platform, cross-language plotting tools. But just in general, there's an ever-growing and very, very good tools set for doing data analysis in Python. Focus, Scikit-learn has some goals that they're devoted to, and while it's a very broad library, they've tried to keep on focus and not get distracted by things that don't really make sense to the library. Among other things, they've tried to keep the tools it has to be fairly general purpose but extensible, so if you want to apply it to some domain, that's up to you as the programmer, and applying models and things across different domains. This is also maybe a debatable point. Scikit-learn scales to most data problems. You have memory limitations with Python. That's becoming, that's changing as you can go on EC2 now and get a machine with 128 gigs of RAM or something just from the comfort of your living room and run your code on that machine remotely. But this guy in his Twitter handle, this big data, says that Scikit-learn scales with most problems, so I'm sure he must be right. But I think that's a partial truth, I guess, is what I'll say. But there's more and more you can do, but that's not infinitely true. Some problems call for distributed solutions, and Scikit-learn isn't really, at this point, your solution for that.
You can use joblib with Scikit-learn too.
Yeah, so, right, and I don't actually know a lot about that, and maybe if there are more questions, you can say something or but there are various ways to...
Joblib actually comes packaged with the Scikit-learn.
Right. Yeah, so there are some ways just beyond native Scikit-learn to extend it to distributed systems and things. Okay, so two things this talk is not. One is this isn't an introduction to Python. There are lots of good resources for that, and I don't think this is the right time or place for that, but I think you should, if you've programmed at all, you should be able to follow the code that I have in here reasonably well. The other thing, this isn't an introduction to machine learning, so if you don't know a lot about machine learning, I'm probably going to use some terminology that you don't understand. I would just ask you to try and pay attention and pick up the things you do understand. And again, if you want to learn machine learning, reading the documentation of Scikit-learn actually isn't a terrible place to start. So instead what I want to talk about is why I think Scikit-learn is a really nicely designed piece of software, and why that design is conducive to solving machine learning problems in a very elegant way and very statistically valid ways, and in ways that are just nice to program. So we're going to look at that. Here's a very basic example of something you can do with Scikit-learn. It has some data sets built into it, or that you can either get that are on your disk, or that you can download from the internet through the datasets submodule. This is Fisher's iris data, which probably most people know about. I'm just selecting the first two iris types, which is target equals 0 and target equals 1. So it's a binary classification problem. We have 4 different measurements of some flowers that were collected 100 years ago, and we want to predict which flower these 4 measurements describe without knowing the flower type. So the first 5 rows look like this. The 4 measurements on the first flower measured is 5.1, 3.5, 1.4, and 0.2. And all these first 5 rows are flower of type 0. And I think in the official Fisher's data it has the names of the iris species, but I don't know them. So what can we do? Well, we can say, I want to create a linear discriminant model to discriminate between 2 classes, and I want to take my X matrix, which is my measurements of the flowers, and my Y vector, which is the classes, the output of the model, and I'm going to fit that linear discriminant model to this data. Everyone cringes as I then use that model to then predict the data I just trained the model on, and we find out we get this perfect confusion matrix. The model can perfectly predict which class each flower is in. So that's bad statistics, but you can see that's at least a good linear discriminant model that seems to be training correctly. Something that may be unclear from a programming perspective is that Python is object-oriented, so all this information is living inside this LDA object, which is an instance of the capital LDA class. And so when you train the model, all that information is living inside this LDA, which is why I'm not catching anything after I call this method to fit the model. And then there's a method on the model called predict that once I've trained it, I can predict from it. Any questions about that?
Are those methods pretty standard through Scikit, that you have a fit method and a predict method?
I'm really glad you asked, Brian. I didn't even pay Brian to ask that. So Scikit-learn has a really nice implementation to where it has 4 main interfaces, and interface is an object-oriented programming term that doesn't actually apply to Python. You don't have interfaces in like the Java sense or C++ sense in Scikit-learn. But these are basically classes that you inherit from. So everything you create in Scikit-learn implements these in some kind of way. So almost everything in Scikit-learn has a fit method, and a fit method we'll talk about more. Is sort of what makes something an estimator. So you can fit this whatever model, and we'll see model gets used very generally to the data, and then you can do some kind of inference given that fit. Things can also be predictors. So given a fit model, you can call predict on just some data without targets or without outputs or dependent variables, and you can predict based on the model that you train. And this data here, unlike the example I just did, this data that you're predicting doesn't have to be the same data that you fit the model on. It just has to be in the same shape, or the same number of columns in your matrix. You can also transform things. So what might be a transformation If you do a principal component analysis and you just select less than n principal or m, less than all your columns of the best principal components, you might transform, or in that case, project your data onto the principal components. Another thing is you could do a variable selection, say, give me the best variables, and you get a new matrix based on the variable selection, things like that. And we'll see there are some actually slightly more complex transformations you can do. The final thing you can do, and Mrs. Stanley, my 10th grade English teacher, wouldn't be happy about the first 3 words ending in R and the last one not ending in an R. But you could be a model, and a model is basically implementing the score function, which is a way, given this estimator we've trained, can we get some kind of score as to how good the estimator is. So the rest of the talk mostly is going through what these things look like and how these play out and how these become valuable. I think that this isn't, looking at Scikit-learn this way, though there's some discussion of it in the documentation, this isn't really how it's presented as a tool. And this isn't the first thing that people talk about. But I think if you understand this, it allows you to use Scikit-learn in its fullest capacity in very powerful ways, and writing really elegant and small amounts of code to solve problems. So that's the big picture of what I'm here to say, is that making things work in this paradigm is a really well thought out programming decision. That something can be emulated and something that can be taken advantage of in writing in Scikit-learn. And I think this, to me, is a difference of using Scikit-learn versus doing machine learning tasks in R, which I'm very comfortable in R, but I've never come across anything in R which is sort of a unified framework of machine learning. And so you have this very nice repository of R libraries. And so if you want a random forest, or you want a logistic regression, or you want a neural network, anything, you can always go and find that. And often install .packages works much better than pip install in Python. And so you can get your thing installed very quickly, but you almost without exception have to go read the documentation and understand how that library works in R, and understand what shape does my data need to be to go in, what am I getting out of it, et cetera, et cetera. And if that works for you or for your given problem, that's great. In general, I've really grown to be very attracted to this very clean interface that you have at Scikit-learn. So if it has the models you need, you can write code that for very different problems might look very similar to the code that you wrote on the last problem. Or you can implement a random forest regression that looks very similar to the logistic regression you just did. And so maybe all you have to do is change your estimator object, this OBJ. Even more than that, you can do dimensionality reduction or do some sort of pre-processing step that also looks exactly like fitting your model, which is pretty cool, and we're going to see in a minute, have some really neat effects. Any questions on that?
Yeah, does it have tools for sort of diagnostics? Like, that's one of the strengths of R is, you fit a regression model, it may have totally invalid conclusions because of some assumption violation, and there's like lots of diagnostics available to find that out.
I'm not sure I have a good answer for you.
Okay.
I'm not a statistician, so I don't have to worry about that.
That's scary.
Yeah, I think that I'll work for you anymore, Gail. I think that's a good question. Yeah, it's something I'd like to explore more and have a better answer for you.
Okay, great.
I don't know off the top of my head. Anybody else have a comment on that? Or sorry,
question on that score.
Yeah.
So my familiarity with Scikit is there's a metrics package and
Yeah.
you load that and you take your, let's say your true and your predicted and it gives
Yep.
you the score. Are you telling me that all the classifiers or regressors have like scoring built into them, or you're just saying in kind of an
So,
abstract way?
If it has a
metrics
score
package?
function, a score method, it has a default scoring function. But you can change what scoring metric
Okay.
you want to go along with that from that metrics package. Or you can define your own.
All right, so each one has its own scoring kind of default.
Yeah, so I think for like a continuous thing, it would be an R squared value. And maybe accuracy or something for discrete values. But then you have complete control over that.
Right.
All right, so an estimator, we've already talked about, is something that implements the fit method. So this is from the documentation. It fits a model based on some training data and is capable of inferring some properties on new data. So I think the genius of scikit-learn, I didn't say what I thought I was going to say, but is that almost everything is an estimator. And that doesn't just include statistical models. So it does include statistical models. So logistic regression, we can create a logistic regression model. We could have added different parameters to it. See down here it's actually printing out. This is the output from running this command. It's printing out the parameters that it's setting by default. But then you can fit a logistic regression to this x and y, which is still our iris data. But we are by no means limiting ourselves to logistic regression as that which, or I'm sorry, statistical models is that which implements the fit method. So that was the supervised learning example. K-means, it's an unsupervised. The clustering method also implements the fit method. So we can create a K-means model. I want to tell it the number of clusters I have is 2, because I know that's the case in this problem, and I can fit that to just my X data. I don't need the Y data. So that's nice. I mean, it change a couple words, and you've changed from a logistic regression to a K-means. Dimensionality reduction, as I've already talked about, you can create a PCA model, tell it the number of components that you want to get out of the model is 2, and then you can call PCA.fit exactly like we had done logistic regression.fit, K-means.fit, and we are training our principal component model, which essentially means doing the SVD to figure out what our PCA model is. But again, a very similar construction on our code.
I have a question.
Yes.
What does it do with missing data? Does it only operate, does it on
Let's not talk about that.
another problem?
So yeah, so it's not as nice as it could be, but there are.
Is it different
some
from
ways.
R in the way it works?
Well, I mean, like R, so there's not just a generic way that R deals with missing data. That depends on what library you're talking about.
It does have an estimator, a fit method for computing data.
Yeah, so you can do things like you can impute data or something, but
If
probably.
you don't, I'm just wondering if it just deletes any record with missing data on one or more variables.
Yeah, I'm not 100% sure about that, but
Well, it depends on the model.
yeah.
Only if you're using decision trees, but it probably would.
Yeah, I'm sure there are better answers out there for that than I have. But this is a good question. So something that's also interesting, so in our logistic regression, we did fit.x, logistic regression.fit xy, and then everything else since then has only needed the feature matrix, and so we've just done fit x. Well, it's going to turn out it's going to be important later that we can actually put a y vector in there anytime, even if it doesn't use the y vector. So the principal component analysis completely unsupervised, but if you want to put a Y vector in there, by all means, you're invited to. And that is done largely for reasons we'll see later. So you can also do feature selection. If you want to select the k best features out of my 4 features, I can say select k best, k equals 3. And again, I can do fit x, y. And in this case, we need y. Okay, so we saw supervised learning, unsupervised learning, dimensionality reduction, and feature selection, all with almost the exact same code that you could do find and replace and just change a few words in your code, and all of a sudden you're solving or you're doing a very different operation. In fact, this is just a variable, the first k best. You could leave that variable. You could change select k best to k means, and you'd still have k equals 3, and it would still run. Very, very small amount of change to solve a very different problem. All right, so that's estimators. Any question? Oh, well, here's just a summary of all 4 of those together to, again, reiterate this similarity in the interface. Any question about estimators? Yeah.
So R has this like really complicated formula language that I'm sure you've used, and some models it doesn't really pertain to, others it does. Like, but if you're fitting a regression model, you can have interaction terms. I assume here you just need to like include that in your X matrix basically, or is there some way of passing it? Like
there's a Python library called stats models that's been working on a formula tool, though it's just by the language construction, it's not quite as clean as the R, because that's standard R.
Yeah.
Actually, don't do much regression in Scikit-learn, and so I'm not 100% sure. Anybody know a better answer to that? I didn't come prepared to answer any questions, apparently. Except Brian's. Yeah, so in theory, in my mind anyway, you could implement, you could have a fit method, basically, that's doing that transformation for you, so you don't have to create your matrix.
Okay.
But yeah, I'm not sure. I'm sure there's also resources out there on how people address that. But I mean, that could never be as nice in Python as it could be in R, by the fact that you can just write random letters in the middle of the function in R without having quotes around it.
Yeah.
Which, I mean, in Python it basically have to be a string, or you'd have to instantiate a bunch of variables to do the formula with.
Okay.
But I know stats models has worked on doing that as strings, basically.
That question does kind of like draw that bright line, though, between machine learning and statistical modeling, right? Because Scikit-learn is really a machine learning, and so you're not, inference doesn't seem to be its focus. It seems to be a lot of prediction, which is where it looks like that idea that you have an estimator and you have and out of that estimator you get a fitter. I've already forgotten all the terminology.
Right. Yeah, so I think that's a good point. Although, from machine learning perspective, you could think about a formula as just like building your features, right?
Yeah.
So, just from a purely pragmatic perspective, you can.
And in R, I mean, that doesn't really enable anything that's not possible via other means. Like you can build all your features manually, and then you'll get to the same place.
But I mean, I won't deny it's a very clean way to. I mean, it's a nice.
Yeah.
If that's what you're doing, it's a very nice thing to do. Yeah. Question?
Now, one thing I was wondering, what's the k-means fit doing? For me, it would be more intuitive to do the k-means predict, because there's nothing to fit. To the clustering.
So, you still have to learn what your centers are. Right. So that's what it's doing.
You fit and then you fit.
Ah,
Right, so so it's probably pulling out the centroids is what you're saying.
Yeah, so as soon as you fit it, you have the centers, and you can say, tell me what the centers of my clusters are.
And you said the Y is just thrown away, it's ignored there, right?
Yeah, it is. And right, so, and that's for reasons that are still to come, so you won't leave the talk early. So actually, I think I have the k-means here, but so what can you do with an estimator? I was thinking I was done with estimators, but one more slide. So with the logistic regression, once you fit the model, you can pull out the model coefficients, and so you can think about log odds and what those mean in terms of how the measurements relate to the outcome. With k-means, you have the cluster center. So I said I have two clusters here. And so these are the centers in four-dimensional space of these clusters. For principal components, one thing you can get is the explained variance by projecting into the PCA space. So you have a explained variance for each principal component that you're getting out, and you could have gotten all four principal components as well. For select k-best, I'm saying get the best, one best feature, and I can ask what's the support, and it's just giving me a logical vector saying that the third feature, the third measurement is the best feature. Who's a good statistician and knows what the third measurement is? Anybody could have just guessed and everyone would assume that that was correct. All right, so is that it? Well, that's it with estimators. Sorry for how small that font is. But it turns out that this fit method is really just introducing us to the world that allows us to do predict, allows us to do scoring, that allows us to do transformation. So among other things, you could think, well, explain variance of the PCA is nice, but I actually want to get my PCA matrix out of that and be able to use that to train my logistic regression or something. So the next part of the API was the predictor. We can fit a logistic regression, again, to the same data, x and y, and then I just have two test instances. I think these are just the average values across both classes, I believe. And then we can predict which class they're in, and as we might expect from the average value, the average of the 0 class is in class 0, and the average of the first class is in class 1. There's actually, I think, I can't remember exactly, but I got burned here recently. They changed how they implemented something. I think predict always wants a matrix instead of like a single vector. And one time I was like basically mapping the predict function over an array of vectors, and it turned out that's after they changed something in Scikit-learn that took way longer than it would if I called predict on the whole matrix. So anyway, the moral of that story is you want to try and predict as many things as you have to predict as possible. You want to do them all together as opposed to doing them in series. But that's kind of off topic, but that it's probably a lot of hours wasted to get on debugging that. You can also predict the probabilities if the model supports that. Obviously, not all models do, but so you can get the probability from the logistic regression, and these rows sum up to 1, so it's the probability of being in one or the other class, which I think is done for consistency. It's kind of annoying in the binary case, but it's done for consistency in case you have more than 2 classes. Some of the models you have to enable this. So with support vector machines, there are ways to get probability that you wouldn't necessarily. And I know with the SVM models, you can sometimes tell it, do a little more computation and get me probabilities. So that's a predictor. I mean, That's pretty straightforward, I think. Another thing we can do is transform things. So that we get this transform method, and that what transform means depends on what the particular model we're talking about. Typically, transformer is not going to be talking about an actual learning algorithm, though I mean, maybe PCA is a learning algorithm, but maybe transform doesn't make sense in the case of a logistic regression. But sometimes there's some surprises that essentially anything can have a transformer if there's some way in which that makes sense. So sometimes there are transformers when you think there wouldn't be. But for a PCA, if we want two principal components and we want to project our data into those principal components, we want to be able to get out a matrix of those two principal components, and that's exactly what we do. So we fit our model, we call fit X, and then we transform X, so projecting into the principal component space. There's also, if something implements transform, it also implements fit transform. And sometimes that doesn't matter other than to save you code, like we have in this case. We have 2 lines of code instead of 3. Sometimes there might be instances, and I actually don't know off the top of my head where this happens, but that fit transform is actually much faster than calling fit and then transform. And there are actually instances where fit doesn't do anything. And so transform and fit.transform are the same thing. So, for example, well, I mean, you could think like, if I'm just going to always take the first column of my data, and that's what my transform operation does. You don't have to fit that, you always know what that means. But the API still stays fairly consistent throughout.
I think the fit method doesn't do anything other than store things in the variables, and it lazily does it during the transform step.
Well, so that's not. I mean, so when I showed like the centers of the k-means and things, those are all computed by the fit method.
Oh, okay. Because at least I've seen the code for the other the supervised learning methods, and fit doesn't do anything.
Okay.
I don't know. Maybe I haven't seen k-means specifically, but okay.
Yeah, so I'm not 100% sure about that. But, so if I want to find the k best features where k equals 1, I can call fit and then transform, or I could call fit transform, and I'm going to end up with this feature, which we know from looking previously is the third column. And so that was the case. The computation had already been done by the fit method before we called transform.
When you say that it sets it up to be lazily evaluated,
Yeah.
then to look at it is to evaluate it, isn't it?
Yeah.
Yeah, well, I don't know. Let's not fight about it now. We'll fight about it later. So the fourth part of the API was the score function. I'm diverting here to using this dummy classifier. So a dummy classifier is used as a baseline classifier, and it's just randomly assigning outputs. And I did that so I could get an accuracy of about 50%, because the problem is, I'm not sure if this data is linearly separable, but it's at least very close, and so I would just get 100% accuracy with any model I put on this this data, the 2 classes of the Fisher's iris data. So anyway, by default, the score function is scoring for model or predictive accuracy. So we're just randomly guessing this is 0 or 1. We're going to get about a 50% accurate prediction. However, as I was discussing a little bit previously, there's a lot of other built-in options for scoring functions that you can choose from depending on your problem, and you can also create a scoring function that you can you can define your score to be whatever you want it to be. All right, any questions about the API? That's going to bring us to the maybe the penultimate section of the talk.
I just want to say that score is sometimes used to mean predict, so it's really confusing. Like people talk about scoring a model, and they may mean generate predictions on it. So they've like twisted the language a little bit here.
Well, I mean, that's not the
Yeah.
getting statisticians and machine learning people to talk to each other is hard. So, and you know, economists have their own language, so you just can't win with that. I think.
When you call the fit function,
Yeah.
do any of the models that you're familiar with automatically do any cross-validation or subsetting within the fit?
Yeah, so sometimes, and so we're going to talk about cross-validation here in a minute, but so I think random forests have some aspects of cross-validation in the model fitting. And there's, so one of the nice things about the API that I'm not going to talk about a whole lot, but you can build anything you want on top of this API, and then you can do computations in Scikit-learn using other parts of Scikit-learn as long as you're implementing the necessary parts of the API, the fit or the transform. So if you wanted, you could also like extend any model to include some amount of cross-validation in the model fitting.
Sure.
But what we're going to see is that cross-validation, part of the nice part of this API is it makes cross-validation an extremely easy thing to do. So you can do it outside of the model fitting very, very nicely.
So when you're doing the four methods that you were talking about before, are you getting things out in a specific class, like a scikit class or something like that, or is it just a matrix or whatever is relevant for the output?
So it's whatever is relevant to the output. So you always have the model object, which has a bunch of properties of various things. But for example, like the transforms, I think almost universally, their output is going to be a NumPy array or matrix. So all this is, for those knowledgeable about Python, is all built on top of NumPy. And I tried to hide a print statement. This is actually one place I failed. So this array here is indicated this is a NumPy array. It's for the data structure. I tried to make this, I erred on the side of being a cleaner presentation as opposed to Pythonic in some ways. You'll see, if you look at the full IPython notebook, for example, I hid all my import cells. So anyway, there's a little more code actually involved in it. You'll see in the slides. All right, so pipelines are something that I used Scikit-learn for quite a while before ever touching the pipelines. And after I started using them, really regretted all the time I spent, and particularly all the code I wrote to do things that pipelines handle very, very elegantly. So pipelines are, in a sense, the big culmination of what this nice API does. If you've ever solved a machine learning problem, which I think a lot of people here have, or maybe even a statistics problem, you know that typically you don't get a nice matrix of data and a nice vector of outputs, and you say, here, your entire problem is just to find a model that does this prediction well. If you did maybe participated in the early days of Kaggle, those are the only times you ever got problems that look like that. You want to do some preprocessing, you want maybe to do some dimensionality reduction, you need to do some data cleaning. If you have text data, you want to run away, but if you can't run away, as you'll see on the next slide, this can even handle text data. So pipelines are going to allow you to combine multiple steps of a machine learning problem all in one little piece of code. All right, so what does that look like? Well, say we have this same data, again, our Fisher's iris data, X and Y, and we want to, we decided this is a good model for some reason. We want to select the 3 best features in our data out of 4, and then we want to just take the best principal component, and then we want to fit a logistic regression on that, a univariate logistic regression on that data. Okay, what can I do? I can define this thing called a pipeline, which is a part of Scikit-learn. And the pipeline basically just takes a list of operations. And in this case, we're giving it these 3 operations: select k-best, PCA, and logistic regression. And we also have to give each of those operations names, which we'll understand a little bit more in a minute. All right, and then we have this pipeline object. So if you ignore this part of the code, there's no data here. All we're doing is defining this pipeline, right? It's very, I mean, there's nothing happening. We're just grouping 3 different objects together: select k-best, PCA, and logistic regression. One thing to note from the Python perspective is that this is a list. It's not a set in particular, but the order of this matters. So if you've used Enterprise Miner or another graphical machine learning thing, what we're doing is dragging on this select k-best block. We're dragging on the PCA block and then drawing an arrow from select k-best into PCA by just making it the next one on the list. We're dragging on our logistic regression and drawing an arrow in code form. Okay, well, once you've done that, what you actually have is another Scikit-learn estimator. So we've taken these 3 things, which are estimators on their own, and we've created a pipeline, and this pipeline is itself an estimator. And what does it do as an estimator? It implements the fit function. So we can call pipe.fit and plug in our data. Notice we didn't say anything up here about the data. In particular, the dimensions of the data don't matter to this pipeline as long as these are conformable, this matrix is conformable to the vector. On top of that, it's also a predictor, and it's a predictor because the last item in it is a predictor, the logistic regression, and so once we fit our pipe, we can do a prediction. And I didn't do a confusion matrix, but you'll be happy to know that that's a perfectly predicted data, so it must be a great classifier.
That is so slick, though. 3 things I'm going to do, and
we're just getting warmed up more.
Could you have chained that though? Could you have let it left evaluate? Do you know what I'm talking about? So like, you've got your methods there. If you had passed the select k-best data, could you have then called the PCA components method on that, dot PCA
right.
components dot?
Oh, well, so for one, Python doesn't handle chaining well because it doesn't handle line breaks well like that. So then that's the Pythonic answer. So each of no, it wouldn't work.
Okay.
And this isn't JavaScript, right? Yeah, so the fit function actually returns a copy of the object, and so
that's fine. I'll take your word for
yeah.
it. It doesn't work. You can tell me over beer later.
Goodbye. Yeah. So yeah, I mean that's just not the Python way of things. So what is this doing on the inside? Well, every time you call fit on a pipeline, it's saying take this data, pass it to the first item in my pipeline. What do I want that to do? Call fit and transform, or fit underscore transform. That's going to output something, a new x vector. The y vector is going to stay the same. Call fit transform on our PCA, so we selected the k-best and did fit transform. And we keep doing fit transform all the way down the chain until we get to the last one. Logistic regression transform doesn't make sense, so in our last one we're just going to call fit, which is what we did here. And then typically, and it doesn't have to be this way, but typically your last item is also going to be a predictor, right? Some kind of supervised model. But I guess maybe typically is wrong, because if you want to do unsupervised, that's fine too.
So your pipeline is not full of methods, it's full of objects. And then
It is full of
calling
objects.
the fit on that whole pipeline, it magically determines the appropriate methods to call on the objects in the pipeline.
So all this is doing is taking this object, calling the fit underscore transform
Okay.
method, and then passing it down. And in good Python fashion, these aren't. So Scikit-learn, you can inherit from these estimator and the transformer and the predictor, which is a nice way to do it. But I'm pretty sure that all you actually have to do is implement this method, and it's going to look for that method, try and call it, and hope it spits out the right thing. It's not going to check, and then it's going to pass whatever it spits out onto your next method. So one advantage, as I was saying a minute ago, is you can implement anything that has a fit method, and you could toss it into your pipeline. Something you might want to do then is implement an estimator, which is really just some sort of transformer to, for example, transform non-numeric data into numeric data in your first step. And I think maybe the next slide shows that. Any questions about this before?
So the fit function doesn't return anything, it just modifies the pipe object in this?
It actually returns a copy of the whole estimator object, but fit doesn't return like a matrix, for example.
Yeah, because you don't assign anything to the variable.
That's correct.
So that's why you cannot just chain like dot the method.
Well, so it does return a copy of itself, so meaning the whole estimator object. So you have there is something returned, and you could come up with some ways of maybe chaining something, but that's not really what it's built for.
So what happens if you put a pipeline together and somewhere in the middle you're supposed to have an array, and what you're actually pipelining into it is a vector?
It's going to throw an exception.
But it won't throw the exception until you get fit or predict?
It depends on where the error happens. Probably it'll
I
happen
would
on.
expect it to blow up in the fit.
I think it'll happen on fit.
Okay.
Rohit was maybe disagreeing with that, but I'm
No,
pretty sure.
I mean, I don't know.
Yeah. But I mean, as is kind of the Python way, everything's just going to assume that it's getting the right data structures, and it's just going to keep passing it down, and it's kind of up to the programmer to ensure that you're passing the right data. It's never going to be checking data types, for example. It's just going to try and find those methods that you need. Any other questions on this? Okay, so something else we could do is a text-based pipeline. This is something I spent a lot of time on when I was at RTI, using Scikit-learn to do predictive analysis on text. As I said, it's a terrible thing. You should try and avoid doing it if possible. But pipelines in Scikit-learn can save you tons and tons of code. I deleted a lot of code after I realized I should have been learning or using pipelines. So one of the famous examples in text prediction, there are about 3 text data sets that all examples are based on. And one of them is news group data. So these are from like Usenet groups. And we can get this is fetch 20 news groups is a part of the data sets module, submodule in Scikit-learn. So anyway, we can get some news data, and we can get some targets, and so these are each post is from one. I'm not old enough to know what do you call that group? News group, I guess. Yeah,
News group.
Yeah. So there are about 11,000 different posts in here. So just so you see that here are the group names, these 20 different groups. And so each post comes from one of those groups. Here's an example post. I have Win 3.0 and downloaded several icons and the BMPs, but I can't figure out how to change the wallpaper with the icons. Any help would be appreciated. I think my mom wrote this morning.
You don't disparage the wrong.
So what can we do with that? Well, I don't really want to go into a lot of the details of text analytics. So if people have questions, I'd be happy to try and answer them. But one of the things you can do with text is count vectorization. So you have, you can think about each post as, if you tokenize it, so split it apart into words, you just have a list of a bunch of words, and you want to get that into some sort of matrix format so you can do some prediction on it. Well, one thing you can do is just count the occurrences of words in that post and do this vector. So each cell in the vector represents a word, and the number in that cell is the number of times that word occurs in that document. And you have as many columns as you have words in the whole 11,000 different documents. So you get a lot of columns there. Just for the sake of memory, I said limit that to 100 different words, and I can't remember exactly how it determines how to limit that. It probably doesn't do the 100 most frequent, because that would actually be bad. You get a lot of A and B and various capitalizations of those. So this count vectorizer is taking in a list of documents, so a list of strings in the Python terminology, or something that behaves like a list with things that behave like strings anyway. And so it's taking in a list of strings and it's outputting a NumPy matrix, or just a numerical matrix. So we went from text to a matrix, which we're all much happier to deal with. Another thing you can do with text is to kind of normalize it, the TF-IDF. So you can think of a word occurs frequently in every document. It's probably meaningless in terms of classification. So the word the occurs a lot in the English language. It's not going to help you determine whether or not something's about atheism or Christianity based on usage of the word the, or if it did, that would be an interesting paper. You should publish it. So you can normalize by term frequency, which is what we're talking about here. And then inverse document frequency, for each document, we want to divide by the, oh boy, someone explain this? I just, we want to divide by the number of,
how often it appears in the document divided by how frequently it appears in documents in general or something.
In the corpus.
right,
And you take a log transformation.
right. So, anyway, I wasn't coming prepared to talk about text analysis, but basically normalizing this to hopefully get better predictive power. All right, so we went from text into our count vectorizer. We got a matrix out. We put a matrix in called fit transform on it, and we got another matrix out of the same dimensions.
Wouldn't you do TF-IDF first and then vectorize it afterwards?
So you can't,
Because once the words are gone, how are you supposed to do TF-IDF?
well, every column still,
Oh, it still
yeah, so TF-IDF is a bag of words model. So, I mean, all it's depending on is just the word counts. Anyway.
Oh, just the count. So the vectorizer does that?
Yeah, the count vectorizer is counting words. In reality, if you're doing this in Scikit-learn, you would actually call TF-IDF vectorizer, which is just going to combine these two steps. But I wanted more code to talk about poorly. So, all right, so we went from text to a matrix to another matrix, and if we have a matrix and we know what categories these things are, maybe we can do some kind of prediction on that, and in fact, we can do this gradient descent classifier, and I'm actually not 100% clear what that model actually does, but it works for multiple categories easily. So we can take in our matrix, and we can take in our categories, which are these 20 different Usenet groups. And we can call pipe.fit on our data, which is a list of documents, and then our y value, which is a list of categories, Usenet categories. And we've trained, at this point, a predictive model on these text documents to where we can just pass more text documents into pipe.predict, and it's going to, when you want to predict, it's going to pass it through the count vectorizer, pass it through the TF-IDF transformer, and then call the predict method on this gradient descent classifier. The alternative is you do all of this manually, to where you have tons and tons of utility functions that are doing all this transformation, getting your text in the right format, making sure every time all of your columns line up so that the columns correspond to the right words, all this stuff. And you write tons and tons of code, and it's full of bugs, and you just start banging your head on the desk. And it's terrible. I've been through this. And when you get to instead write 5 lines of code to classify text, it's a really magical thing. This becomes even more important when you want to talk about cross-validation. We'll talk about it in a minute, maybe next. Any questions there? If you're not excited about this, you've clearly never done text analytics. This is a bit of an aside. If you've used pandas in Python and you've used Scikit-learn, you've probably been disappointed that Scikit-learn doesn't handle pandas very well. And so pandas is a data frame, and you can have data in more formats other than just a numerical vector. And Scikit-learn doesn't really have any functionality to know how to deal with a pandas data frame, so you still have to have your own step at the beginning to get your data frame into at least something that looks like a matrix. It can still be a data frame, but you can't, for example, have categorical data typically as the input. Or in Scikit-learn, you could have categorical data as long as you have all categorical data, but mixing it up doesn't work as well. There's actually, this isn't part of Scikit-learn natively, but someone's built a Python module to help deal with this. It's a tool called Scikit-learn pandas, and it essentially tries to implement some of this Scikit-learn API on something that works nicely with pandas data frames. So I can have a data frame mapper that's basically going to map my data frame into a NumPy array. So I can map, this is the same format as the pipeline, although the order doesn't matter so much, and you'll see in a minute. But I'm saying this is just named pet. The word pet isn't doing anything. But I want to, oh, I'm sorry, actually, this is selecting the column pet, and I want to binarize that column. So what you can see is I went from cat, dog, dog, fish to a 1 in the first column for a cat, a 1 in the second column for a dog, a 1 in the third column for a fish. For my children column, I want to scale that. So subtract the mean and divide by the standard deviation, or whatever you do to scale things. And for the salary, I just want to do nothing. So I'm putting a Python none, which is it's like a null, passing it in there.
So when you say PD, do you mean the Scikit-learn pandas?
So this is just a data frame. This data frame mapper is part of Scikit-learn pandas. And I intended to hide as many modules as possible. The PD is getting us a data frame object. So I created this data frame mapper, and basically it's a fit transform, or an estimator transformer in Scikit-learn terminology. So I can add this mapper into a pipeline, and so I can map my data into this numerical matrix, which is what I had right here, and then pass that into a principal component analysis and get 2 principal components. And so I can call my pipe on this data, and I've used the word data several times here as a variable. This is a pandas data frame that has categorical and numerical data, and I can call pipe.fit transform and get a principal. You like that, Ryan? You like
cool.
Yeah.
It's all right.
And I can do a principal components analysis on my categorical and numeric data mixed. If you've used pandas and you use scikit-learn, you haven't used this, I think it's pretty cool to see together. If you haven't used either one, it maybe isn't as interesting, but this also saved me a lot of steps. And again, when you come to cross-validation, this is really valuable. I have no idea how long I'm supposed to talk.
You get another 15 minutes and then they come to take us away.
Okay. So that was created by a guy whose name is Paul GB on Twitter. If you've seen this map where Facebook did this friend connection map, Paul actually made this when he was an intern at Python. He's like an intern at Facebook. He made this in R. And he's now a freelancer in Toronto. Super nice guy on Twitter and has fixed all the bugs I've ever reported in Scikit-learn pandas. So I like him very much. But this is just like entire map created by mapping friend connections on Facebook. So he didn't draw any continents here. That just appeared out of the data, which is pretty cool. Some Facebook data science recently made an updated version of this. This was a couple years ago. All right, we're going to blast through this most important part here in 15 minutes or less. All right, so how can we use all this for model evaluation and selection? I keep talking about cross-validation. Let's deliver something here. All right, I'm using another part of Scikit-learn to create a random data set, which is pretty cool to be able to do. I'd actually never used this until this talk, but it's quite handy for demonstration purposes. So I'm going to create a classification problem that has 1,000 samples, has 40 features, so 40 columns. Only 6 of them are informative. The other 34 of them are just random numbers that aren't correlated. I guess they're all random numbers, but not correlated to the outcome. And I want to have 2 classes on my outcome. All right, so hopefully that makes sense to a lot of people. I'm going to build a really simple pipeline, which is select the k best features, and we would hope the best number of features to select would be 6, right? We only have 6 informative features, and then we want to classify it with just a naive random forest classifier. So what we can do with this pipeline is do cross-validation on our model, and I guess I'm leaving out here that, so this is a well-defined model, and these all have, I guess select k best needs a k value. Maybe it defaults to all of them, but if you gave parameters to this, you could cross-validate and get like a cross-validated score. So jumping the gun a little bit, but instead what we can do is get a cross-validated score on a whole bunch of models with different parameter configurations and pick the best model out of all of them. So for example, this is why we had to name our parts of our pipeline. We can say, I want to try all these different k values. So select is the name of my select k best step in the pipeline. Select double underscore k, and I want to try 1, 6, 20, and 40. And classifies my classify step, and the parameter I want to change is the number of estimators. So this is the number of trees in your forest for your random forest. And I want to try 1 tree, which is like a decision tree, 10 trees, or 100 trees. And so I can take this pipeline, which is, I mean, you can think about this as like a class of models where you can change the parameters. And I want to try all these different parameter combinations in this pipeline and cross-validate that. And you can give as much specification as what kind of cross-validation you want. I don't think it probably defaults to 3-fold or 10-fold or something like that. But you can do, there's actually very, very powerful cross-validation generators depending on what makes sense for your problem. And so I can search across all the possible parameter configurations and find out which one's best. So if I call, this is, again, grid search CV is an estimator. It implements fit, and it's going to implement fit, in fact, on a whole bunch of separate models. If I have 4 parameters here and 3 parameters here, how many different models do I have? Right, 12 models, 4 times 3, not 4 plus 3, which is important. And so I can fit this, and it's going to try all these different models and cross-validate it, so it's going to fit every model multiple times and score it on the cross-validation holdout sets. And then I can say, what's the best parameter configuration? And it tells me the best thing I can do with my random forest is choose 10 trees, which seems about good enough for a random forest. And very happy, it actually says to select 6 variables. And we know we only have 6 good informative variables in this data anyway. And then once we have that, this grid search object has a best estimator object, and we can use that best estimator to make predictions. So we searched over all these models, and we got a good one, and now we can make predictions with it. Unfortunately, we get the curse of dimensionality, as we just talked about. You have to multiply all the parameters, and in fact, you can see here that you can dump all the output, everything computed. These are the means of the cross-validated accuracy scores. These are the standard deviations, which may very well be interesting to you, and these are the various parameter configurations. So you can see that some of them are quite good, like if you have 100 estimators in your random forest, and you have, well, here's the best one we had was 0.9. We had 10 estimators in our random forest and 6 variables. Well, some of them are quite poor, like if we just say, have a decision tree on the one best variable, we get an accuracy of 0.72, which in this case isn't that good, though in some problems that would be really nice. So there, I guess that's really me talking too quickly about something that's extremely powerful to do. We're building models and checking over a bunch of different parameter configurations and getting scores and choosing the best model in very, very clean way. And I'm unfortunately jumping straight from there to some more boring technical details of how we deal with the curse of dimensionality, but on the other hand, this is also implemented nicely in Scikit-learn. So there are a few things we can do, and there are actually even more than I'm mentioning here, but these are kind of the easy things you can do. One is you can distribute these across multiple cores, so these computations fitting each model are like embarrassingly parallelizable. So if you have a bunch of cores in your machine, or you can get an EC2 machine that has 64 cores and a lot of RAM, you can just tell this grid search how many cores you want to use with the n_job parameter. Here I gave it a whole bunch more parameters, so the number of combinations it has to choose increases exponentially because you have to multiply these things together. So I say just do it on one core and fit it, and it's going to take about 6 seconds. I can say do it on 7 cores because I have 8 cores in my shiny new laptop. And it's going to do it in about 1.8 seconds. And if you thought it should have been 7 times faster, you're naive about parallel computation. You should fix that opinion. That doesn't mean, but sorry. The other thing you can do is randomization. So I studied optimization in grad school. I hate how machine learners are very fast and loose about optimization, but anyways, that's the way it is. But one thing you can do is you have this huge grid that you want to search across, and instead of searching across all of them, you could just say, let's just search at some of the points. Maybe some of them are good, and there's a little bit of intuitive reason why you might say that, is that often if you look at your grid scores, there are a lot of models that give you good results, and if you start to think about your standard deviation on your cross-validation scores, there might be a lot of models that are statistically indistinguishable in terms of model quality. And so you might think, well, I computed all 12 of these. If I just computed 5 of them and looked at the best, maybe if I'm lucky, I'm going to get a good output from that. So we can do that by, so this is just a grid search again, which we had done previously. It might be slow. In this case, I entered 40, I guess that's actually 39 parameters there and 99 parameters there, so whatever 39 times 99 is, that's a lot of things it has to search over. That's going to take a while, though. You can see my computer did it. It's probably a few minutes. Alternatively, I can change my grid search to a randomized search, CB, so CB for cross-validation, but I can say limit the number of things you search to 10. So instead of doing 39 times 99, which is a big number, I'm just searching 10 of them. In this particular instance, my cross-validation score went down from 0.924 to 0.894 by searching over a much, much smaller space. And I didn't do the times here because it would have taken a while, but in a fraction of the time. I mean, I guess in this case, this is reasonable guess that it would be 39 times 99 divided by 10, which is 400 times faster. It would be a reasonable guess in this case. So that's an option, but you're reducing the number, the space that you're searching over. Any questions about that or about grid searches? All right, so again, I feel like that was a little too quick in that grid searches are sort of the climax of model evaluation and model selection, but if you just want to take a single model, you know what your parameters you want to be, and you just want to score it, you can do that too in this very nice way. Again, where essentially you're chaining together estimators and you're creating other estimators like your grid search. You can create an estimator like a cross-validation scorer, which you can fit on your model and get some kind of score out of that. Which brings me to my conclusion. Scikit-learn has an elegant API, which is what I really tried to emphasize in this talk, is that this is really well thought out, and it makes, if you're using it to its fullest extent, it makes code very, I think, enjoyable to write, and it's very maintainable because you don't just have tons of crap to deal with all the cases of cleaning data and preprocessing. You can put it together very nicely, and it's also in Python, which I think is a really nice language, and I definitely have criticism of Python, but for me, it is a very enjoyable language to write in. I've written in a very large number of languages, and Python is definitely one of my favorites to write in. Sometimes when I run it, I regret that, but it is very nice to write it. Pipelines allow complex chains of operations to be easily computed. You're not supposed to put new points in your conclusion, but one of the things is cross-validation can be really hard to do if you're doing things like dimensionality, reduction, or various things that if you choose your best variables and then you do cross-validation on those selected best variables, you're doing cross-validation wrong and you're deceiving yourself. Statistically, what you need to do is your cross-validation on the whole set of things. And if that doesn't make sense to you, Elements of Statistical Learning is a free PDF, section 7.10.2. You can read that, and you may still be confused, but they tell me that that's the resource to go to. But doing cross-validation well, simply from the mechanics of getting your code together and doing the whole chain of operations that needs to be done for correct cross-validation is hard to do in most machine learning environments, programming environments, I think. And this is by far for me the least painful way I've ever done it. In R, I usually just give up. So. Finally, pipelines combined with grid search make for really easy model selection. So you can think again of a pipeline as being a whole space of models, and you can search over that space of models for the best model. All right, we have 3 minutes, 1.5 minutes for questions. And I'm happy to field questions later by email or Twitter, or that's about it. Anything?
Data set sizes and speed. Have you had any experience with kind of really big data?
What's really big data?
Terabyte?
No, this isn't the right solution. Yeah. What is? I mean, yeah. you do a gradient descent model on some really simple thing that you could implement on Hadoop.
I might have a suggestion on that. I know that PY tables is I know that Pandas integrates well with it, but it's a layer to access a hierarchical data format. So it's basically, if I have not enough memory space for this data set that I would really like to operate all in memory. So it kind of abstracts that so you can save your data to disk and then swap it into and out of memory as it's needed to perform your calculations. So you can, that's a way of getting around my data set is large.
In big chunks, I'm assuming. Yeah.
Yeah.
Nice.
So that would be another.
Yeah, and I mean, you could imagine like splitting your data and training models that you can then average on. But yeah, I mean, there's just nothing's pretty on terabytes, machine learning on terabytes of data at this point.
I guess another thing that I would bring up is this library is built on NumPy, which is the Python numerical array sort of library. And a lot of your other statistical and mathematical libraries that Python have and extensions are using the same thing. So if you have some other library that does something of interest and you can get an array out of it, you can use that as input to your, things from Scikit-learn or extensions that other people have made from that. So it makes everything very portable if you can leverage things that others have done.
And you can get the Fortran compiler to install NumPy on your computer. Then it's easy.
Am I allowed to put your Twitter handle up here?
Yeah, it was on the slides, absolutely.
Something else to put in the big bag of triangle analysts. Okay, TV Hopper on Twitter. And, yeah. Which is actually correct, right?
Correct.
TV Hopper, and Twitter feed is really good, actually. It's got a lot of great stuff on it.
Thank you, Melinda. I hit 20,000 tweets this week, so you can at least be entertained.
We are going to go to the Cameron Village tap room for the after party, which is right around the corner. I did not warn them, so they're probably going to have to split us up if we all descend upon them at once. But we'll buy beer, so they'll be happy. On the meetup group, let us know how you like this venue, assuming we can get more space, right, a larger room. Let us know how this time is working for you, and let us know if this is a long, long drive. I know it's a long drive for Ian. And we should really find a spot in Chapel Hill once in a while. So if anybody's got a favorite place in Chapel Hill to do this, let's try that. Thank you guys for coming. It's wonderful to see you. Thank you so much.
Literally around the corner. Right.
I must know.
I enjoyed it.